What's up guys, and welcome to this video on the 2019 supplementary exam, physics exam. Basically the aim is to go through from 2019 backwards all the way to 2015, going through the subs and the final exams. So for today's video I will be doing the MCQ section. There's 10 questions. Okay, what I always recommend is that you do the MCQ last, because the MCQ is made to trick you, or it's designed to make you think a little bit, and it's much easier once you've actually done the basics throughout the exam to just see if they're trying to trick you or if they're trying to mislead you in some way. But for this video, we're going to start off at the MCQ, so let's get into it. Okay, so answer the following cool stuff. Okay, so which of the following pairs of physical quantities contain scalars only? Okay, so what is a scalar? We need to understand. Scalar has magnitude only, no direction. Okay, cool. Velocity has a direction, so that goes away. Acceleration is a vector. Work, speed, okay, this is a candidate. And displacement and velocity, both of these are vectors, so our answer is C. So 1.1, the answer is C. Okay, cool stuff. So question 1 done. Then we have a ball which is dropped from a certain height above the ground and bounces a few times as it hits the ground. The velocity time graph below describes the motion of the ball from the time it is dropped. Ignore the effects of air resistance or air friction. Okay, is the relationship between the velocity time graph of the ball. Okay, so which is the following? So basically we need to understand what's actually happening. Okay, so let's draw a little displacement time graph kind of, and let's think about what's happening. So this is the point from where it's dropped. Okay, and when it's dropped, it's going down immediately. Okay, so let's say that it's dropped from some height h, and so it drops. This is point A. Right now, it's going down, it hits at point B, and now it's moving upwards, and it goes from point C. Again, this is exactly where it is, and this is point B and C, and it goes to point, it goes to point D. Okay, that point right there. At point D, the velocity is equal to 0, and at point D, we see that it's going to turn around again. Okay, so the question asks, okay, so we know that it's moving downwards. So down is taken as negative. Down is taken as positive, so that cannot be an answer, and down is taken as positive, that cannot be an answer. The next question we need to ask is, the height, is its maximum height at C or D? And from our diagram, we can see it's at that point right there, which is point D. So that's wrong. So 1.2, our answer is B. Cool stuff. When two objects collide in an elastic collision. So what does elastic collision tell us? That EK before is also equal to our EK after. Okay, so basically conservation of kinetic energy. So here this is an option. Momentum is also conserved, but is it only conserved? Maybe, but that's an option. B, both impulse. Okay, so impulse cannot be conserved. Impulse is constant, but is not conserved. And we know that both momentum and kinetic energy are conserved in this situation because of this elastic collision. So for any collision, momentum is conserved. And for this specific elastic collision, kinetic energy is also conserved. For our answer for 1.3 would be A. Cool stuff. Okay, so in a certain electric field, the direction of the electric field is to the right as shown. Okay, so how do we define, or what is a convention, right? The electric field tells us that the direction that a positive point charge would move. So if we have a positive point charge, it would move rightwards. Okay, so the question now asks, which arrow shows the direction in which an electron, so an electron is a negative point charge, would move. So if we placed a negative point charge, it is going to move that way, B. So it's going to move to the left, so answer for 1.4 is going to be B, because it's the opposite of the direction that a positive point charge would move. Okay, then we have electric charges with magnitudes Q, 2Q, 3Q, and 4Q are placed in different electric fields. Okay, we've got the forces, and we want to know the greatest, which charge experiences the greatest electric field strength. Okay, so we need a formula to help us for this. Okay, so electric field strength is equal to, we can say, F over Q. Okay, and if we carry out, so we can essentially assume that Q is the same for all of these. So we can say that for the first one, it's going to be 55. E is going to, okay, so let's actually make a table. Say E. Let's continue this table. Okay, so here it's going to be 55 divided by 4, Q, 3 divided by 30, oh sorry, rather the other way, 30 divided by 3, Q, here we have 25 divided by 2, Q, and 20 divided by Q. Okay, and which one of these is the biggest? Okay, 55. So right now, my initial gut feel is that this one is the biggest, 20 divided by Q. 55 divided by 4 is equal to 13.75. 30 divided by 10, 25 is 12.5, and this is 20. So our answer is 20. So it is going to be 1.5. The answer is D. Okay, cool stuff. The next question, we say a cricket ball of mass 160 grams. I'm going to convert this immediately to kilograms because that is our SI unit. It's traveling at 25 meters per second, right? So this is our cricket ball. Then it's hit by a batsman and leaves. So this is before, this is after. Okay, so we want the change in momentum. So change in P is equal to M change in V, which is equal to, we're going to take right as being positive. Our mass is 0.16, and our final is going to be 35 minus 25, because 35 is, let's actually take the final direction. Let's take left as positive. Okay, so then that's a positive value and that is a negative value. And when we crunch the numbers, what we get is change in P is equal to 9.6, and the units kilograms meters per second. Okay, so the question is, we only have one answer, so it is that one, and it is definitely moving left. So 1.6, the answer is B. Cool stuff. Okay, the role of a step-up transformer in an electric station. Okay, so first of all, so heat, okay, so let's read the first one. Reduce heat in the transmission lines by increasing the voltage. Okay, so firstly, we use step-up transformers. Step-up is always related to voltage. Okay, so step up means that we are increasing the voltage. So anything that has to do with current can go away. So we're left with A and C as our options. Then the next question is, why would we step it up? Okay, when we're carrying electricity in the power grid, we want to reduce the heat loss. Okay, so we want to reduce the losses. So then we're left with one option right there, which is A. So question 1.7, the answer is A. Okay, so a kettle with a power of 2000 watts is used for a total of 20 minutes per day, assuming that the cost of electricity is R1.80 per kilowatt hour. The cost in rands per day. Okay, so what is the cost? What is an expression for the cost in rands per day? Okay, so our final answer we want as being rands per day. So that's how I'm going to work. Okay, so we have to work towards this unit. Okay, so we start off with 2000 watts. okay, and we multiply it by 20 minutes per day, okay, times 1.8 rands per kilowatt hour. Okay, and I want to end up with rands per day. So I want this unit here to remain the same, and I want days to remain the same. Okay, so I want to get rid of this hour, and the way I do that, or I want to get rid of this minute. Okay, and the way I do that is I say there is in 1 hour there are 60 minutes. Okay, so that we can say the minutes cancel each other, the units of minutes, and the hours also cancel each other. Okay, now I want to get rid of this kilowatt. So times, so in 1 kilowatt, we have 1000 watts. Okay, so the kilowatts go, and the units of watts also go. So the units that we have left are days and rands. Everything else is cancelled. So now the question is, what are we left with? So we're left with 2000 times 20 times 1.8 all over 60 times 1000. Let's see if that's one of our options. That's not that one, not that one. There you go. Cool. So the answer is C. So question 1.8 is C. Okay. Question 1.9. The magnetic flux through a loop of wire changes are shown in the sketch below, during which time interval is the induced EMF positive and non-zero. Okay, so let's first think about our equation. So what equation could we use? We could use the equation EMF is equal to the negative number of coils, change in flux, over change in time. Okay, so it says it wants non-zero. So where are the zero values? So the change in flux over change in time is 0. Okay, so the change in flux over change in time is 0 over here. So we can't use that place there, and we can't use there. So we can't use B to C, and we can't use D to E. So we're left with two options, these two options. Okay, so now we see that our formula for EMF is in negatives. So N is always positive, obviously. So minus, a minus number times, we're looking for a change in flux over change in T to be negative, so that our answer comes out as a positive, because that's what we want. So change in flux over change in T is our gradient. Okay, so there we have a negative gradient, and here we have a positive gradient, and so we want this situation where we have a negative and a negative, and that is right there, so A to B is our answer. So 1.9 is A. Cool stuff. And then the last question, the name of the law used to determine the direction of induced current in a conducting coil which experiences a changing magnetic flux is Faraday's law, Fleming's law. This is just a theory question. It's not Faraday's law. It's not Fleming's. It's not Fleming's motor or dynamic law. So we're left with Lenz's law. So 1.10 is equal to D. Okay, so let me just quickly write out the answers. 1, 2, 3, 4, 5. Okay, 1.1, 1.2, 1.3. Okay, and 1.6. Okay, so in summary, we had C, B, A, B, D, B, A, C, A, D. So those were our answers. Okay, guys, I hope you guys see that these aren't too difficult. There are some times where we need to think a little bit, but others are just straightforward theory questions. So yeah, thanks for watching, and I hope this helped. Okay, cool. Thanks for watching, guys. Cheers.